So one of the first topics usually studied in physics is kinematics, or the study of motion. And in order to understand this, as well as many other topics further down the road in physics, we first need to understand how vectors work and what they are. Before we define vectors, let's first go ahead and define scalars. So scalars are quantities that may have units, and most importantly, they describe numerical values. So in physics, some of the most common scalars that you'll find include mass, volume, and time. And the reason why these are scalars is because you can describe each of these with just a single number. So for example, if I asked you what the mass of something is, you could respond 40 grams. For volume, you could say 3 centimeters cubed. For time, you could say 10 seconds. And so these are all just a single number. And if you wanted to conduct operations with them, it would be quite simple. For example, if I wanted to do maybe a mass of an object minus the mass of another object, I could do 40 grams minus 30 grams, and that's 10. And the same applies for addition, multiplication, and division. The only important thing to note is that obviously the units have to be the same. So now moving on to vectors. The difference between vectors and scalars is that vectors have both a numerical quantity and a direction. So we can define vectors as quantities that describe a magnitude and direction. And so some common vectors that you'll see throughout physics are velocity, displacement, momentum, and a variety of other forces. And so the way we represent vectors visually is just using a simple arrow. So with the arrow, the direction of the arrow represents the direction of the vector. And the length of the vector represents the magnitude of the vector. It's important to note that the length of the vector is not necessarily equal to the magnitude of the vector. What it more means is the length of the vector is proportional to the magnitude of the vector. Because, for instance, this arrow literally is probably about 1.5 centimeters. So that's the literal length of that vector. However, it could represent something like 5 meters per second, which is a velocity. So if we were to draw an arrow twice as long, this would represent 10 meters per second. Once again, that's velocity. So some important notation for vectors. When we want to write a vector, and let's call this this vector here on the left, vector A. We write it with an arrow on the top. And this just means vector A. Vector A. If we wanted to describe the magnitude of the vector, there's a few ways it can be written. Like this, or sometimes you'll see it with just these absolute value looking signs. And both mean magnitude. Magnitude of vector A. And the magnitude of vector A will always be positive. Alright, now that we know how to physically represent and refer to vectors, let's go ahead and start vector operations. So the first important vector operation is vectors multiplied by scalars. And so, as we remember from before, a vector both has a magnitude and a direction. And scalars just have a magnitude. Now let's say we have vector A here. And we want to multiply it by a scalar 2. What this does is, because the scalar only has a magnitude, it won't affect the direction. Instead, you're essentially multiplying the magnitude of the scalar to the magnitude of the vector and leaving the direction alone. So what this would look like is just a doubling in the length of the vector, and this would now be 2a. So you can kind of imagine it as 2a vectors stacked on top of each other, both pointing in the same direction, because the direction is not affected. So direction is not affected when multiplying vectors with scalars. The next operation will now be dealing with two vectors. So we're going to start with vector addition. So first, there's some rules we need to understand about vector addition. The first is that they must have the same units. So you wouldn't be able to add something that has, say, units in meters per second to something that has newtons as the units, because it just wouldn't make sense adding them. The other thing we need to be aware of is that, unlike vectors and scalar operations, we need to take direction into account. Direction needs to be taken into account. Because, unlike before with vectors and scalars, two vectors now each have their own directions. that need to interact with each other. So for example, if we had vector A, that looks like this, and we had vector B, that looks like this, and we wanted to add vector A plus vector B to get a resulting vector, vector C. Well, the easiest way to understand how to do this is to visually add the vectors. And so we'll call this method the tail to tip method. So the tail to tip method refers to two important parts of the visualized vector. So I'm going to go ahead and copy vector A over here on the right side. Go ahead and label that vector A. So the part of the vector with the arrow is known as the tip, and the part of the vector on the other side is the tail, which is pretty intuitive. And so for the tail to tip method, we'll first draw out vector A, and then we'll go ahead and draw out vector B and place the tail of vector B to the tip of vector A. And so what that will do is that will allow us to draw a resultant vector from the tail of vector A to the tip of vector B. So our C vector will look like this. So the addition of vector A and B will result in vector C, which will then form a triangle. And so sometimes you're given some values that correspond to this triangle, and you may have to use the law of sines or the law of cosines to further analyze this triangle and get some unknown values. Alright, so that was vector addition. Now we need to cover vector subtraction. So this one is a little trickier than vector addition, and we'll see why. So unlike vector addition with the tail to tip method, with vector subtraction we use the tail to tail method. So once again, if we go ahead and draw out a vector A that looks like this, and a vector B that, let's say, looks like this. If we want to do A minus B, which equals C, the tail to tail method means that we take vector A, go ahead and copy that over here. We go ahead and take vector B, and we put the tails together. So unlike vector addition, where we would put the tail to the tip, in vector subtraction, we put the tails together. I'll just get that more centered up. Okay. So I'll go ahead and label this vector A. And go ahead and label this vector B. Now, one of the most confusing parts about this is where exactly you draw the C vector from. Because In the previous example with the vector addition, we know that we draw the c vector from the tail to the head. But in subtraction, we're left with two heads. So the rule you need to know for this is that the resultant vector is drawn from the negative vector to the positive vector. So what I mean by the negative vector is that in this problem, b is the one on the right side of the negative sign. So I'm referring to b as the negative vector, and a is the positive vector. So when we draw the resulting c vector, we draw it from the negative side, which is b, up to a. Now an easier way to solve this without having to use this rule is converting the vector subtraction into vector addition and using the tail to tip method. So once again, I'm going to go ahead and copy these vectors down. And let's go ahead and take another look at this equation. What we can actually do is rewrite this as a plus negative b equals c. So by assigning the negative sign to b, we're essentially reversing the direction of the b vector. So if I were to write negative b, the vector would now look like this. So the magnitude of the two vectors stay the same because b stays the same. All we're doing is we're adding a negative sign which rotates the vector 180 degrees or flips it. And now we can add these two vectors together. So if we have I'm going to get this precise, so I'm going to copy this over. Let's move that over here. And then let's get b. I'm going to put that tail to tip, just like in vector addition. This is a, and this is negative b. And now we can draw our resulting vector. Just like before we learned, it goes from the tail of a to the tip of b. And you can see here that in both cases, the c vectors are the same. So no matter which method you use, you'll always get the same answer. Alright, now that we understand basic vector operations, let's talk about vector components. So we can always think of a vector as a sum of two or more perpendicular vectors, depending on whether you're in 2D or 3D. So I think the best way to visualize this is if I go ahead and draw a graph. And let's say we have a vector that looks like this. What this really is a sum of a horizontal vector going like this and a vertical vector going up like this. If I wanted to prove that, I could, like before, do some vector addition and prove that a vertical vector like this added to a horizontal vector like this will result in this diagonal vector. Now when we label vector components, let's say of vector A, we write them as an x component and a y component. And the reason for this is because, like here, the horizontal vector goes along in the x direction. So we call this ax. And the vertical vector goes in the y direction. We call this ay. So essentially, this a vector is the sum of these two vectors. So I'll go ahead and just draw that clearly here. So we have the vector A. We're going to have one component like this. That's the AX component. We have one component like this. That's the AY component. So we can see here that this forms a right angle triangle with with vector A is the hypotenuse. And so with this in mind, we can write out some important formulas. So hopefully you've seen this before. So what this means, if you haven't, it's sine means it's opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And so if we go ahead and label this as theta, I'll go ahead and use a thinner pencil for that. Let's go ahead and label that as theta, and we can label that as phi. So with that in mind, we can write sine theta is equal to ay over a, right? Because this is opposite, and this is the hypotenuse. Same thing for ax, we can say cosine theta is equal to ax over a. And if we wanted to use this angle instead, we could also say sine phi is equal to ax over a, and cosine phi is equal to ay over a. So sometimes in problems, you'll be given components or you'll be given the vector, and you'll want to go back and forth between them or solve for unknowns. And so these equations are going to be very useful for that. Now with these vector components, there's some new vector notation, or vector notation. So more ways we can describe vectors. So for example, A, we can write that as ax, ay. So just like how we can express a point as an ordered pair, we can do a similar thing for vectors with its components. And keep in mind they're expressed in these greater than, less than looking brackets. Now, if you wanted to represent the magnitude of A using these components, that would be the square root of ax squared plus ay squared. And this is just basically Pythagorean theorem, right? If we look at, once again, if we look at the triangle, and this is A, and this is ax, and this is ay, you'll remember Pythagorean theorem states that a squared plus b squared equals c squared, or c is equal to the square root of a squared plus b squared. And so that's how we get this. If we wanted to, if the vector was in 3 dimensions, we would basically just go ahead and add, let's squeeze in right here and add an az component. And here, we'd write az squared. Now, for this next part, I'm going to go ahead and draw out 4 quadrants. Because vector components can be negative. So not everything exists in this first quadrant here. So say we had a vector that looks like this. Now its ay component is positive, but the ax component is negative because it's going in the left direction, right? The negative direction. Similarly, if I had a vector like this, the y and the x would both be negative. And so you may get something that looks like -2, -4. And all that means is a vector here, -2, we just count -2, -4, find that point there, and it's just a vector that looks like that. So that is that. Now let's say we have this graph, and I plot a vector here in the 4th quadrant with theta as 30 degrees, and the magnitude, let's call this vector A, the magnitude of vector A as 5 meters per second. And I want to find the components ay and ax. So if we recall the trigonometry I showed earlier, we can say that ay is equal to a, and when I write a here without the lines, just know I mean the magnitude of a. So a sine theta. And for x, a cosine theta. Now there's one thing that I haven't taken into account in these formulas, and that is the direction of the vector components, because the vector components can either be positive or negative. In this case here, we can visually see that the y component is negative because it's going down. And the x component is positive. So to compensate for that, I have to put a negative sign here. So if I go ahead and solve this, negative 5 sine 30, 5 cosine 30, that should get me negative 5 over 2 and 5 square root 3 over 2. We can write our units. And now we can go ahead and write this in proper vector form as 5 root 3 over 2 negative 5 over 2. And so this vector, this notation effectively represents this vector that we drew here. Now, let's say we want to work through this backwards. So let's say on a problem, instead of giving you the angle and the magnitude of the vector, let's say they give you the vector components. We'll go ahead and use these same components here. And let's say they ask you to find the angle between the vector and the x-axis. In this case, we know it's 30 degrees, but we want to go backwards from the component form to the vectors. So the way we would do that is using the tangent equation that I showed earlier, which looks like this. And then if we rearrange it for solving for theta, ay over ax. So let's go ahead and input our known values. So after solving for this, we get theta is equal to negative 30 degrees. Now, at first look, this doesn't make sense because we know the angle has to be positive. And the reason why it is negative in this case is because the range of arctan is from negative 90 degrees to 90 degrees. So because of this, we have to modify our formula to take the absolute value of ay and ax instead of just solving it normally. So any negative values that appear are going to go away. And with this, you'll always get a positive number. Alright, so that's it for vector basics. I think next time I will cover dot product and then start going into some kinematic equations.